Assalamualaikum everyone. So we'll start with the next lecture on compass reversing. So first we'll talk about some temporary adjustments of the prismatic compass. So like you have done in the lab, the temporary adjustments consist of fixing the compass with a tripod stand and then forming the reasonable height of the tripod stand so you can see the reading clearly. And then we have centering, which basically means placing the compass center exactly above the station point. This is very important whenever you are taking angles or bearings in this case. So the center of the instrument has to be exactly above the station point, and you can do this by using either a plumb bob or by dropping a stone from the compass center. And if it strikes the station point, that means it is exactly above it. And then we have leveling. So the instrument has to be approximately leveled because whenever you take bearing of the compass, so the needle moves freely until it adjusts itself. So in order to have that free movement of the needle, the instrument has to be leveled. Otherwise, if it's tilted, that would mean that the needle is striking the any object, the compass box, because it is balanced on a pivot. So that is why leveling becomes important. And then you have adjustment of the prism through which you read the bearing, and once you have done all that you can observe the bearing. So we'll talk about two different types of compass. One is prismatic compass that we use in the survey lab, uh, and as the name suggests, this prismatic compass, so this is because of this prism, which is an added feature of this instrument. So you do not note the reading directly of the needle or the ring. You read it through the prism and then you see the reflection, and that is why we don't have 0 degrees at the north on the compass, because you're reading it off a prism. And then the other type is a surveyor's compass. So as you can see, no prism in this instrument, so you have to note the reading directly of the needle. And the other difference is that the prismatic compass has a whole 360 degrees graduation, whole circle bearings, and in survey compass we have quadrantal bearings. And since we note down the reading directly, we have 0 degrees at the north and the south, and 90 degrees at the east and the west, since it is quadrantal bearing. Now let's talk about our prismatic compass, the different components of the compass. So we have this compass box which holds the whole assembly, and then we have the pivot on which the magnetic needle or the ring is balanced so that it can move freely. Then we have the magnetic needle, which has the graduations on it, with 0 degrees at the south, and then we have the prism over here through which you can note the reading that gives you a reflection of the needle. And above that, we have this red and blue glass. So these are there if the light is not ambient and it's not possible for you to clearly note the reading. So you can use them just like we use eye shades when the light is bad so that you can note the reading. So the two are for different lights. Then we have this object vane or the side vane over here, which has a horseshoe or a thread in the middle of it. So using this, you can sight the object. And then you have this adjustable mirror. So that is if you are working in a terrain that has a varying topography. So the land is not plain, and due to a difference in height levels between where you are standing and where the object is, it's not possible for you to see or view the object without tilting the instrument. So that's where this adjustable mirror comes in. So even if your eye level is not in line with the object, you can see a reflection of the object in this adjustable mirror, and that would give you an idea that your instrument is in alignment with the object that you are trying to view. Then we have this brake pin over here. So since the magnetic needle is placed on a pivot, whenever you move this assembly even slightly, the whole ring keeps on oscillating for some time. And obviously you can't wait for it to stop oscillating and then to note down the reading. So that is why we have this brake pin over here. So it's like a button. Whenever you press it, so it applies brakes on those oscillations and this needle becomes static and you can easily note down the reading. So these are the parts of the prismatic compass, and we have discussed surveyor's compass already. And let's now discuss this other phenomena which is called as depth of the magnetic needle. So as you know that the compass points towards the magnetic so magnetic north or the true north. Well, we have discussed that point in detail as well, that it should point towards the true north, but it actually points towards the magnetic north. So since it tries to align itself with the geographical north, so if you are performing survey somewhere in the northern hemisphere, so your needle, since it is placed on a pivot, it will dip towards north. And if you're working in the south, it will dip towards the south. So it won't be completely horizontal. Due to the magnetic effect, there will be this dip in the needle, and this that is called as dip of the magnetic needle. Then we have to talk about a very important thing which is called as local traction. So uh, your compass points towards the magnetic north or the true north because it is magnetized by that. But if you have some local magnetization, so that influences your compass, and your compass won't point towards the true direction in which it would point had there been no local traction or no local magnetization. So if your needle comes near some substances such as iron ore, steel structures, or powerhouses, so it's found to be deflected from its true direction, and it doesn't show the actual north. So this disturbing effect or this error, the additional error, is known as local attraction. And how you can pinpoint that if there is local attraction is that we have discussed that whenever you take bearings of a survey line, so over here there would be forward bearing and over here there would be back bearing. So the difference has to be equal to 180 degrees. And if this difference does not come out to be 180 degrees, that means either you had some error in noting down the readings, or there was some personal error, or there was local attraction, either at both the station points A and B or on one of them. So this is how we can check if there is local attraction or not. And if there is found to be local attraction, error due to local attraction or error due to some other causes, we can apply some correction. So the first method of correction is that if you have a closed traverse, that means a series of interconnected lines that form a loop. Since it takes the form of a closed polygon, so we can apply this check, which is that the sum of interior angles should be equal to 2n minus 4 into 90 degrees or n minus 2 into 180 degrees, where n is the number of sides of the polygon. So whatever sided polygon you have, n, the sum of the interior angles should be equal to n minus 2 into 180 degrees, and the sum of the exterior angles should be equal to n plus 2 into 180 degrees. So this is a check for interior angles and exterior angles for a closed polygon. But this is for closed traverse. If you have an open traverse, we have some other uh, checks for that. We will discuss that in the next lecture and when we study light traversing. But for closed traverse, we have these two very simple checks. And then we have the check that we discussed, where the difference between forward bearing and back bearing has to be 180 degrees. So that check is just for when you use in compass. The first method applies both for theodolite and for compass, but the second method that applies strictly for